Okay, James, you can take it away.
Great. Good afternoon, everybody. Good morning, good evening, depending on what time zone you're in. Welcome to the in-memory virtual chapter meeting for March. We have a very exciting presentation for you this afternoon. Our speaker is George Walters. But before we have George start, we're just going to go through some past community news here for you from March 2016. First of all, the past Business Analytics Conference 2016 is coming up in May. It's going on May 2nd through the 4th in San Jose, California. If you haven't registered, please register today. All the information here on the slide will be presented to you once the presentation is over. As always, if you want to be involved with more SQL information, we have all these virtual chapters out there. Please register for them. They give you a wealth of knowledge. They each hold meetings just about every month. Here are the upcoming virtual chapter meetings for March. High availability and disaster recovery. Some of these have already happened. The one that's coming up is Global Hebrew SQL Server Reporting Services 2016 on steroids. That's coming up on the 14th. Actually, I'm sorry, that is already over. Today is the 15th. Upcoming SQL Saturdays. These events are always a good time if you can make them. For North America, we have Boston, Richmond coming up on the 19th. In April, we have Redmond, Huntington Beach, and Colorado Springs. International, Exeter, Belgium, Nepal, Vienna. All these are great if you can make them. If you have never been to a SQL Saturday, I highly recommend you attend one. The knowledge you get there is it's invaluable. PASS would not exist without a global network of passionate, dedicated, and hardworking volunteers. Everybody with PASS is a volunteer. If you're interested in helping out with an in-memory virtual chapter or your local user group, volunteer today. If you go to volunteer.sqlpass.org, it gives you all the information you need. Stay involved. Also, anytime you need to look up what's going on for PASS, look at LinkedIn, their Facebook page, follow them on Twitter, follow them on PASS, the website. So with that being said, I am going to transfer the presentation over to George. George, are you ready?
Thank you very much. Welcome, everybody. I appreciate your time today, and I am about to share my screen out. So the topic today is about in-memory tables. There's a little bit on data warehousing towards the end and how in-memory tables affect that. But primarily, this is a TP technology that can help you speed up a lot of workloads. So as stated, my name is George Walters. I'm a technical specialist with Microsoft in the Northeast US District. And feel free to reach out to me on Twitter, @GWalters69. So before we jump into the in-memory specifically, there's a lot of things that have happened lately around the Microsoft platform. In particular, we had the privilege of Gartner, one of the largest research firms, put us past Oracle in the Magic Quadrant. This is important in terms of higher level people thinking about what data platform to adopt. We've also been noted by the NIST, National Institute of Standards and Technology, as having the most secure database platform. That is important also to various things going on around security and what platform should be adopted going forward. Data warehousing performance is off the charts, which is nice. And the rest of this is a little bit of marketing, but coming in 2016, there's going to be some cool features around R being integrated into the data platform. And of course, having in-memory across different workloads. So why is the topic of in-memory coming about? The real deal is that hardware has changed drastically over time, mainly to meet the needs of all the data explosion going on. The cost of memory in this chart is on a logarithmic scale and has been declining over time drastically. When I was much younger, I bought 2 gigs of RAM for $400, or 2 megs of RAM for $400. Now my phone has over 2 gigs of RAM and a 4-core chip. And modern servers can reach out to terabytes of RAM and over 100 cores with commodity Intel hardware. So when you have that sort of horsepower, what are you going to do with it? That, coupled with the amount of data that's being ingested by businesses and businesses trying to get more value out of that data, leads to a lot of challenges. And with that, we may need to research different ways on how to access our data. And by we, I'm actually going to talk about Microsoft. So the biggest feature set announcement that came with SQL 2014 specifically around in-memory was these in-memory tables. It is a different table structure altogether. Regular tables are 8 kilobyte data pages. So you have all of the columns of your data across in rows, as many as can fit on an 8 kilobyte page. This has been the data structure since the early 90s for sure, and maybe even further before that, and other platforms. So when you have that sort of data structure, it makes perfect sense for a system which doesn't have enough RAM to query the data. So it pages data out to disk, it pulls data in from the disk, you have indexes to pull that in, and as you do inserts, updates, and deletes, at a physical level, SQL Server is operating on an 8 kilobyte page. Historically, this has not been very much of a problem. We get faster disks over time, we get more CPUs, and get more RAM, and suddenly we have enough processing power where that physical limit of that 8 kilobyte page becomes a gating factor. So one of the ways we worked around this, the details of how this new data structure, the memory optimized tables, are built, is effectively you can go out to research.microsoft.com and look up David DeWitt, a researcher at University of Wisconsin, who helped us come up with a new data structure. And it was codenamed Hackathon, now it's memory optimized tables. One customer did an early installation of this technology back in 2011 or so, and it was announced at the PASS conference back then. And that customer is bwin. They're a European online gaming firm. And even though they had the 80-core box with many terabytes of RAM to help process these web requests coming in and storing session state for a large number of IaaS servers, effectively this platform that they had was to serve up to gambling, online gambling. Storing that session state was done within those 8 kilobyte pages, and no matter how large the hardware was, they could never get past 15,000 batch requests per second. So with this new style table, again, codenamed Hackathon, memory optimized tables, the data structure becomes effectively a glorified hash index, always persisted in RAM while SQL Server is running. And then there's little bits like delta tables for inserts that come in. Deletes are marked for deletion and cleaned up later so that we get the maximum speed out of this architecture. And just by changing to this architecture, they went up to 250,000 batch requests per second. To be clear, this is a very specific fix for a very specific problem. Those of you who do any kind of performance tuning on SQL Server, one of the many parameters to look at is latch contention. And the different weight stats which are published out there, there's page latch, page IO latch, and things like that. The ones that have IO on them are actually doing operations of those pages to and from disk. And the only way to really fix that is to tune your queries and get your disks faster. But once that page is in RAM on a traditional table, if you get a lot of threads accessing it at once and doing inserts, updates, and deletes, that 8K page can become the bottleneck, like I said, and that's where page latch contention can happen. And on a user table, this feature can help alleviate that specific problem. So that being said, there are some other features that deal with modern in-memory technologies, such as the Columnstore index, which will be for another presentation. But that also leverages the extra memory we have in modern servers, in order to reduce I/O for data warehousing type workloads. So what does this sort of feature look like? So some of the benefits out there, let's just step back a second. The SQL Server engine, when your query comes in from a client application, it goes through the tabular data stream handler, that's TDS, where it handles the network stream, parses out the query stuff. It goes through the parser, and then that says, okay, what sort of, do I have a query plan available? Let me go generate one, and then let me go and figure out how to access those tables and indexes. What statistics do I have? Let me go pick the index to go and seek to my data appropriately, and then I return the result set. That's basically how a query runs in SQL Server. And then inserts, updates, and deletes get written as well, the changes of those physical pages along the way to the transaction log, and then when the transaction is completed, to the data file group. So the buffer pool is this section of RAM within SQL Server which stores our traditional page-based tables and indexes. And then there is the lock manager, so for row locking and table locking and all that sort of stuff. That's a logical gating mechanism, but the latches are the physical storage of data underneath in those pages. So this has worked well for us for a number of years, the modern hardware. We decided to go and add on within SQL Server.exe this whole new area to deal with these memory optimized tables. So your stream of queries comes in the same way. It goes through the parser, and there's a couple of options along the way. So some of the important things that we all know and love about SQL Server is things like full ACID compliance, that's atomicity, concurrency, isolation, and durability. And that's needed to have a true relational database. And that's able to be done with this new in-memory technology. So we can have a query come in, it can get parsed, and we can migrate a table from regular page-based tables to an in-memory table, and it'll have primary and secondary indexes on it. And we will be able to access that just by migrating the table and not changing any code. We gain a couple of options here. Firstly, when we create this table, we have to store it in a separate memory optimized file group. And that table is stored as file stream data. So file stream is a technology that's been around since 2008, generally for large blobs to be stored outside of your database MDF file or NDF file and stored on the NTFS file system. So that's leveraged to store on disk these in-memory table. Once SQL Server starts up and it pulls that table into memory, it builds the indexes on it. And at that point, when it's fully pulled into memory, then we can access it. So our query comes in, goes through the parser, it decides with the procedure cache that, hey, we're going to go and access this in-memory table maybe, as well as a regular table, and we can join that data together and get a result set. And the data access and especially the inserts, updates, and deletes will be much faster on that in-memory OLTP table. That's pretty good. What we have found, though, is that at some point, once we get our storage up to maximum speed, and nowadays that generally means solid-state disk, we have a lot of CPUs happening. We finally migrate our tables with the most contention to this in-memory format. Suddenly, your SQL going through the interpreter, that interpreter of T-SQL becomes the bottleneck. The CPU of processing just T-SQL queries becomes a bottleneck. So how do we get around that? The next option beyond migrating the table is to go and take your stored procedures that access that in-memory table and migrate it to a natively compiled stored procedure. And that effectively turns it into .NET code, and that .NET code is like a DLL accessing that hash index in memory by itself. and then it returns the result set, and then that result set then can be joined to other Transact-SQL against ordinary tables. So that's where that in-memory OLTP compiler on the right side in the upper right part comes into play. That is an option. It's not required, but it will make things faster once you get your tables migrated. The other part is that traditional tables are effectively, as long as they have indexes on them, a hierarchy of these 8K pages. So when you do inserts, updates, and deletes, different levels of this hierarchy of those pages may have to get updated. So we have to do, when you do a begin transaction and an update, a lot of those pages may change along the way. And if a rollback has to happen, that has to be logged to the transaction log for a rollback to properly happen. In memory optimized tables, things are a lot simpler. Effectively, you just have a hash index, and an insert either happens or doesn't. There's no hierarchy per se. It's just each row is unto itself effectively. So then, because this whole side of the equation is optimized for maximum speed, we do optimistic concurrency. We do row versioning so that writers don't block readers, things like that. And then we can optionally have logging to the transaction log turned off. Now that's an advanced feature, and the only time I would recommend that is for operations that truly do not need to be logged for point-in-time recovery. An example of something like that may be a staging table for a data warehouse where I'm doing a big bulk insert and then doing upserts from that table to my other tables. That may help the import process speed up quite a bit, and because that doesn't usually require point-in-time recovery, perhaps I could turn off transaction logging there. If I do keep transaction logging on, I only log the final state of that transaction if it succeeded. If it did not, if there was two updates that blocked each other, one would succeed, one would fail, I would expect my code to catch that failure and then retry again. Retry logic in your applications is a best practice and has been for quite some time, so definitely make sure that that is done for the code that you would use against these tables. So with SQL 2014, it was the first version of these memory optimized tables. It was meant for a couple specific use cases, and we'll talk about 2016 and some of the improvements in a bit. Firstly, the schema is fixed in 2014. When you create the table, it is created and you do not get alter. You don't have any blobs because, again, we're talking about speed and maximum speed for quick, lightweight inserts, updates, and deletes from many, many threads. Lob object type data generally comes from big applications like SharePoint or maybe CRM systems or document storage systems. That generally is not the type of workload where you get the highest speed OLTP operations happening, so that's not part of this scope. In 2014, there were no constraints. All that you had was at most a primary key, and you could have secondary indexes on the table as well. And then no identity, calculated columns, or .NET CLR code. So we're talking a very basic table that's extremely high speed with very little contention ever possible. In 2014, the maximum size of schema and data was about 512 gigs. And the other piece is that compared to a traditional table, this in-memory table with the hash index on it could be 2 to 3 times larger than the row storage you had in a traditional table. So if I had an 8 gigabyte table and I was thinking to myself, I have a lot of latch contention here, maybe I should migrate it to in-memory, then I would have to account for 24 gigs of RAM that might take away from my buffer pool where my traditional tables and indexes are. So you do have to be careful about this. And then finally, the options on durability. The table at creation time, you can declare it to be schema only, where it does not log transactions, or schema and data, where transaction logging does happen. And in this case, because there's a simpler structure, what is logged being that just that final status of succeed or fail, it's a lot smaller of a log record than under a traditional table. So what does a creation of a table look like when we're talking about this? Here is an example where I'm creating a customer table. It has a customer ID, name, and a customer since date time, and then an index. All right. The way you can tell that it's a memory optimized table is the options after the table statement, as well as the index types. So here it's memory optimized equals on, durability equals schema and data, and then the primary key is not just a regular primary key, it's a non-clustered hash, and then there's this funny thing called a bucket count. And that bucket count, again, this is where if you're looking at these memory optimized tables, you have to take a lot of ownership around this. How much data are you going to have? How many rows you're going to have? For an efficient use of these memory optimized tables and the indexes, the bucket count should be approximately 1 or 2 rows per bucket. So to be more clear, if you have an ever-increasing table size, probably not a good idea for memory optimized tables. If you have a fixed table size and you have 1,000,000 rows, then your bucket count should be 500,000 to 1,000,000. That's basically it. So you have to know your data and gain some confidence in what it looks like before migrating here. So that being said, I have a primary key. That's the order of the data, so to speak. And then there's a secondary index that I can specify in line. I do not create indexes after the create table statement. Effectively, the data gets stored as a blob on disk, and during SQL startup, it pulls it in and builds these indexes. That's when the indexes are built. And then we do some maintenance along the way. Now, if I choose to make stored procedures memory, native compilation of stored procedures to access that data directly and bypass the T-SQL interpreter, here's an example script. Create procedure with native compilation and schema binding. Both of those are absolutely required. And then execute as owner has to be declared specifically. And then begin atomic, which basically creates a transaction if you don't have one, or just creates a save point. And then transaction levels. There's only a couple choices, snapshot and I think serializable, and then maybe repeatable read, and that's it. All right. So the goal when they were designing this was up to 100 times increase in throughput. They got close to 30 times under ideal circumstances. The indexes exist only in RAM. And this area of memory for these memory optimized tables is separate from the buffer pool where your traditional tables and indexes you've known for years live. Then we can optionally compile to C code through Transact-SQL statements. It will compile it for you to that native compilation to gain increased speeds. Now, because this is a simplified table structure, there's no locks, no lock manager, no latches, and that's a lot of overhead that's removed for this particular type of table. And of course, we do optimistic concurrency, full ACID support. So for the applications that fit into the narrow band of 80, 60 characters, or say bytes per column, no foreign key lookups or things like that, those sort of limitations, this might be a good place to go. So why don't we do a demo? And the goal here is to solve a lot of threads trying to access a table and causing contention. So that being said, I'm going to pull up my Azure virtual machine with 8 processors. And to prove that, we'll just pull open Task Manager. And then I could do details on this. All right. Okay. And it says 8 virtual processors. Down over here. Okay. So the first part was creating a database, which I've already done. It takes a little bit of time. I'm putting the transaction log onto a solid state disk. So this is an option in Azure. You can pick solid state disks, just like any real cloud provider. And this is a regular table at this point, and there's a stored procedure. The idea in this demo app is it's a ticket reservation system, so we got lots of ticket agents trying to log in and get people airline tickets. And here's the table statement. We do have a constraint primary key cluster, so we do have a primary key on 2 columns. And then we have a stored procedure to insert some reservation details, which effectively does a loop in inserting some data. And we do some batch inserting of reservations. And then we do some reads. That's basically what this app does. So this is with traditional tables. And in this case, we'll just start with this. And I have the details shown on how much CPU we have, and then of course latches, as well as transactions per second. So this is a 28 gig of RAM, 8-core system with solid state disk. I should be getting better than 1,400 transactions per second. My CPU though is only 30 to 50%. That's not so good. And my latches were the top problem in this case. So what can we do about that? We can try and migrate our table to a different format. So the first step is to go and create a file group that contains memory optimized data. We're going to add a file name to that file group. And then we're going to create the table. We're going to drop the existing table, recreate that same table with the same name with the constraint primary key, non-clustered hash with that bucket count we're talking about, and then memory optimized equals on. And then the rest of it is pretty much the same. So let's go execute that. And then, of course, being a demo, we do some fun things. And let's see how fast that works. So suddenly we are at close to 10,000 transactions per second. This is good. We're at an 8 times speed. All I did was change the table. Didn't change the stored procedure at all. My CPU is high. And generally speaking, in a modern application, we tend to tell people, hey, if your CPU is maxed out, then I guess you're doing all right, assuming everything else is fine. I mean, look, the latches are low. I fixed my problem, right? Well, what's happening on the backside is that the table has no more latches. The table is free to go. But my Transact-SQL code, even in stored procedures, regular stored procedures, is interpreted. So let's go fix that issue. And so that's where we change our procedure, our stored procedure, and we do the native compilation, schema binding, execute as owner, begin atomic, transaction level equals snapshot. That sounds good. And so this is just that piece of the stored procedure that does the detailed work of accessing that table. is separated out from the rest of the overall stored procedure. And then there's a parent, the read, and then when I do reading, I also do native compilation in this case because that will increase my speed. And then there's a parent stored procedure that goes and reads the reservations, for example. So while I cannot do a native stored procedure to tie together memory optimized tables and regular tables, I can read with my natively compiled stored proc that memory optimized table, pull that in, and then have that as a subsection of a larger stored procedure accessing other stuff. That's perfectly fine to do. And did I execute that? I should probably execute that. That sounds like a good idea. And let's see what kind of speed we can get out of this. Now we're talking. Again, CPU is at 98 to 99%. Latches are minimal. I have close to 20 times the performance here. And that, my friends, is a good reason in this specific case, this style of application, lots of threads, hitting one table or one hot part of a table and getting latch contention, this can alleviate those sort of issues. I didn't change the hardware size at all, and I didn't add any special disks. I am utilizing solid-state storage underneath, but that's not the gating factor here. So hopefully this makes sense. And then I'm going to switch back into the slideshow. So that's all well and good, and we've had that sort of feature around since 2014 came out. So what is 2016 helping with in this arena? So that we had a lot of limitations in the 2014 release. It was the 1.0 version of in-memory tables. So of course, customers saw it, and they said, well, that's nice, but I've got applications that actually do funny things like, and it's not so funny, things like outer joins, select distinct, subqueries, ors and nots. Those were not supported in 2014. They are supported in SQL 2016. So you can download the RCA 0, Release Candidate 0 of SQL 2016 today and go and use this right now. I actually have Community Technology Preview 3.3 running, which is what I did this demo with. That is, you can spin it up in Azure, download it, run it. So we can do that. We can alter the table. That's good. So if I need to change the bucket count on the table, maybe I had an estimation of 1 million rows and suddenly it's like, oh no, it's not 1 million, it's more like, this looks like 100 million to me. Oops. Well, if I had a bucket count of 1 million with 100 million rows, that would mean 100 rows would be in each bucket, and I could get contention points between those buckets. I increase the bucket count, and the index is utilized more efficiently, and then I don't get the blocking issues there. So I can do full schema changes with alters. I can add and drop columns and constraints. Constraints are there beyond the primary key. Almost a full T-SQL coverage, including user-defined functions. Now the other part is that the original in-memory OLTP, any query that hit it was effectively single-threaded. So it was great for lots of threads that were single-threaded. In 2016, now you can do parallel processing on it as well. And then there's more scalability with more socket systems. So by sockets, of course, we're talking about processors, and processors, of course, nowadays have multiple cores. So we're talking about 4 and 8 socket systems that are these large commodity hardware that's out there. Some other things, MARS, which is multiple active result sets. I know there's only a few applications that use it, such as SharePoint, but that is going to be supported in 2016 for memory optimized tables. And then finally, to gather the data for which tables had the most latch contention, in 2014 you could run the management data warehouse, which is the data collection tool, and get some reports on which tables bubbled up with the most latch contention. So you kind of had to set it up, collect the data, run it, go and look at the reports. Now it's basically going to be a glorified DMV with some visualization on it, and that's what's going to happen in 2016. So hopefully this makes the surface area of what you can use in memory OLTP quite a lot larger, and I think we're going to get more mainstream applications utilizing it. So the alter table syntax kind of looks like this. You can add table constraints, indexes, column definitions. That's all great. Rebuild, just like a normal table. As stated, what's key is this bucket count. The ability to change that makes all the difference. And then the native compiled stored procedures. Before, it essentially was drop procedure and create procedure to change it. Now we can alter it. So this lets us have more uptime. Uptime is important nowadays. And obviously, this is key. So applications are not always static and set in stone. If suddenly I decide, oh shoot, the stored proc, let's see, I might have changed my front-end code. I no longer need C2 selected from my dbo.t1 table. So I can just kind of change my application code up front, still accept the 2 columns in the results set optionally, and then I can go and change the stored procedure underneath to just return that first column with an alter statement. So there's a list of other things in here: right outer joins, left outer joins, all that fun stuff, cross joins. Nesting natively compiled stored procedures. So before, it had to be the top level stored proc for accessing the memory optimized table. Now we'll allow you to nest that. That's pretty good. We can also do grant and deny permissions and select distincts as stated. Group bys with no aggregate functions. That's pretty good. We are also increasing what we're doing with this memory optimized table. We're going to let you mix and match it with other types of storage, such as Columnstore, for real-time analytics. Great. So it was a single-threaded process to persist the memory optimized table. Now it's multi-threaded, so that's great, along with multi-threaded recovery. Apparently they must have hit that as some kind of bottleneck out in the field. Merge operations, that's obviously something that would be great in a data warehouse type world. And then of course more DMVs, looking at the checkpoint statistics and the checkpoint files, and those checkpoint files are periodic files stored with the differences in the data in that memory optimized table, so that you kick the plug and you reboot and you have more of that memory optimized table stored on disk for the restart to pull it all back in. So now we're getting linear scalability on systems up to 4 sockets, which is, we're talking about the HP DL 580s and things like that. Many major vendors view that as a top-notch system. There are some 8-socket systems out there, but it's a lot less common. Then we can actually enable multiple active result sets in your connection string. Just state it. Multiple active result sets equals true. And in SQL 2016, that'll work fine. So back to security for a moment. We've had whole database transparent data encryption since SQL 2008. That's where data at rest is encrypted, and when you query it, it becomes decrypted. The application needs to know nothing about that. Memory optimized tables in 2014 were not encryptable, and in 2016 they are. So this is great. Now that data will be encrypted as well, and this diagram of how to encrypt it is on our website. And you essentially, for those that haven't done encryption yet, there's this thing called the Data Protection API. We start at the Windows OS level, encrypt the service master key, which is just created when SQL starts up. That's done for you. Then we make a create master key, which is going to be the database encryption key. That creates a certificate based on that master key. That certificate encrypts the database encryption key in the user database. So we're going from master database to user database. Then that database encryption key encrypts the whole user database. And then we alter database set encryption on. Quick note, transparent data encryption also causes TempDB to be encrypted. Why? Because TempDB does spools and order bys spooled out to disk, and that stuff gets encrypted. So if you have 1,000 databases and you choose to encrypt one of them, TempDB will also be encrypted, so that could slow down your whole server. Just be aware of that. And what's the impact of TDE, transparent data encryption? I've personally seen it up to 10% for bulk inserts. We say 3 to 5%, but it depends on the workload. And then finally, a new report to help you read which tables need different levels of effort to migrate, as well as how much performance gain. So some tables might have very complex, maybe they got triggers and other crazy stuff. That's going to be in the significant migration work category. Maybe we have some outer joins and it's a simple table with no blobs. That's going to bubble way up to high gain and minimal migration work, things like that. But this report is going to be built into Management Studio to help you diagnose that. So the final piece of the puzzle is, okay, this is great. I've got in-memory tables. They're intended towards OLTP, but my business is starting to think about getting near real-time reporting. We're getting away from a world where we export from an OLTP system and import into a data warehouse and wait for cubes and other things to be built. People that are in charge want results and reports much closer to when the events happen that are recorded in our data. So in 2016, this is what we're going to do. The Columnstore index, which is a different technology intended for analytics, where tables are sliced vertically and horizontally into million-row groups, and those groups get squeezed and compressed and stored on disk, is great for analytic queries. It is not so great for OLTP, however. Inserts, updates, and deletes into a column store, way slower, that's for sure. Single row selects, slower in a column store. But big giant aggregation queries over few columns in a wide table, fantastic. So to get the most out of both in 2016, we're going to allow you to have an in-memory OLTP table that first of all, in 2016 can be much, much larger than in 2014. Secondly, we're going to have filtered non-clustered column store indexes that can be updatable. And that can be on the, shall we say, cooler portion of the in-memory OLTP table for analytic queries that hit that portion. So I'm looking at total sales for 2013 through 2015. That should hit my column store index. Meanwhile, I'm selling stuff right now, and that needs to hit the hot part of my in-memory table, and that's what it's represented in red here next to the in-memory OLTP table. So the in-memory OLTP table is the gray and red, and then the darker red underneath is the column store index portion. And then we can optionally have B-tree range indexes to span the gap between where the column store index leaves off and the in-memory table picks up, in case we need to query that range and get quick responses to the row for that area. Sounds complex, but it allows a lot of up-to-the-moment updates and fast reporting on that data. So at that point, you would insert rows into the hash key, delete, it seeks for which row to be deleted with that B-tree index, and then it goes and deletes the row in the hash index. But in the clustered column store, it marks it for deletion, and then there's kind of like a lazy cleanup process. And then updates, seeks it, and does the update, which is a delete and an insert. And then likewise in the column store index. There's some notes here on CTB2, which is done, where you don't need to worry about the trace flag anymore. So finally, the other part is that in 2016, you can spin up an always-on readable secondary. And by the way, even in 2014, my in-memory tables get replicated to always-on availability group secondaries. That data is replicated to my secondaries. That's good. So I can read from there, no problem. Columnstore indexing, we'll just say got improved, and now that's also in always-on secondaries, fully supported as well. And why are we doing this? Because data warehouses need to get close to real time. And then memory optimized tables getting larger and coupling that together with column store indexes on them for the analytic part, it's like a marriage made in heaven. And then the final bit here is a bunch of other features coming. I'm not going to talk about them too much, just that encrypting data all the way from your application through the pipe into tables is coming in 2016. Polybase, which lets you query outside to Hadoop regions, is coming and pull that data into or out of SQL Server. Quality mobile reporting, reporting services getting a full workover in 16, and then R being built into SQL Server. Finally, as far as cloud integration, those big old tables that are taking up lots of storage, you can spool a particular table out to Azure SQL Database natively with SQL 2016, and it'll spool out those rows and just keep the hot rows local on your SQL Server and then run a distributed query across both places to get your results set. And that's it for my presentation. I do encourage you all to consider strongly checking out Microsoft Virtual Academy. There's lots of free webinars there and quizzes you can take. Channel9.msdn.com is much shorter weekly webinars on different topics. And then, of course, the blogs on the data platform can point you to a lot of other resources. So at this point, I'd love to open it up for questions.
Unmuted.
Thank you, George. It was a wonderful presentation, and I see that we do have a couple of questions. So Dennis asked, is it possible to get somewhere this demo airline ticket reservation driver app project?
That is a fantastic question. This particular project, no, it's Microsoft internal, but on codeplex.microsoft.com, and probably getting migrated to GitHub, which is where we're starting to migrate our stuff, is some demo scripts. So you can demo some of this at some level, but the fancy graphics, that's probably something you'll have to gin up short term.
Okay, great. No, I think that provides an excellent solution for demoing these things. Paresh asks, hi, what about encryption in transport? I think you covered that in the last slide, right? So always encrypted in 2016 takes care of encryption all the way from the client to the server and back, right?
That's correct, yep.
Okay. Ashish asks, will this webinar be available in the YouTube virtual chapter? And the answer is absolutely yes. You can check back in a couple of days and it will be available like all the other previous sessions we have. It is recorded, will be posted. The materials will be posted to the virtual chapter archive page, and it will be available on YouTube as well. Dennis also asks, is always encrypted and in-memory OLTP compatibility in SQL Server roadmap? And I believe
so always encrypted.
Yeah.
Yeah. So always encrypted plus in-memory. The answer is always encrypted does something different from traditional transparent data encryption, where the client driver talking to the application is where you pick the column of the table that needs encrypted, or columns. So you're not encrypting everything, just the sensitive data. And then over the pipe and into the table, whether it's an in-memory table or a column store table or a traditional disk-based table, it's just a different it's just different looking data. It's effectively like 0x7ff whatever instead of my social security number, for example, that gets stored and then retrieved. So it is fully compatible.
Great. I think that handles that. Another question from Thomas, is the bin2 sort order still needed in SQL 2016 for in-memory OLTP?
Bin2 sort order. I do not know the answer to that. That's a good question. I will have to look that one up.
Okay. And Paresh also asks, can you elaborate a bit more about the TDE and TempDB issue?
The answer is in TempDB with transparent data encryption, when you do a big giant group by or order by in your user database, SQL Server under the covers will utilize TempDB at times for that operation as kind of a staging area for sorts and things like that. Because of that, the data pages for that sort operation are literally being stored and persisted for a very brief time, but they're being persisted in TempDB. So because of that, operationally, and this is starting with SQL 2008, when I turn on transparent data encryption in a database, we also encrypt TempDB to protect your data.
Okay. Yeah, that takes care of that question. Any other questions? Doesn't look that way. So thank you very much, George, for a wonderful presentation. And I hope you enjoyed it as much as I did. And I will wish to see you sign up for the virtual chapter imvc.sqlpass.org. Sign up for the chapter, and then we'll send you once a month a reminder email of the upcoming event with a registration link. And hope to see you all again next month in our coming presentation. So I'm going to stop the recording now.